So we're now prepared to make an important definition. This definition is for a basis for a vector space. A basis for a vector space is a list of vectors. It's a list of vectors in that vector space. And specifically, this list of vectors has to have two properties. That list of vectors has to be linearly independent, and that list of vectors has to span the vector space. So turns out that bases have some wonderful and powerful properties with which we will do many great things. Start by observing that it's kind of a balance to find a basis. In particular, you'll recall that we've studied linear independence, and we've seen that the more vectors you have, the harder it is to maintain linear independence. And loosely speaking, the more vectors you have, the more opportunities there are for non-trivial relations, significant relations. So to maintain linear independence, that is easier if you have fewer vectors. On the other hand, in order to span the entire vector space V, you need at least enough vectors to do that. You need enough vectors so that everything in the vector space is a linear combination of your list. So these are competing requirements. You need at least enough vectors to achieve the span requirement, but not so many vectors that you can't maintain the independence requirement. So competing forces. Okay. The reasons why bases are important, we can't go list them completely here. We'll see those develop over some time in this course. But a very quick observation I'll make is that because of the span requirement, every vector in the vector space can be represented with that basis, this short list of vectors. And this ends up being extremely convenient in a lot of situations. So instead of having to write vectors down separately, we can just write them by, in what way are they linear combinations of our short list of vectors. The independence requirement. There's some great reasons we need this. Not one of the best reasons for this requirement is that none of the vectors are unnecessary. We'll see some much better motivations than this for linear independence. But in particular, you recall that if you have a linearly independent list, then you can't remove any of these vectors without destroying the span. Said differently, if you can remove a vector and not change the span, that list is dependent. We proved a theorem to that effect a few sections back. So, in some sense, none of the vectors are unnecessary. There's no wasted, useless vectors. Okay, we'll see more detailed discussion than this about why bases are important. First, an example. Here's a list, and let's ask, is that a basis for R2? And now I've, of course, committed a grammatical mistake of suggesting that this is a plural by use of R. Of course, this should say, is this list a basis for R2? Okay, so again, try to be careful with that, but realize that the grammatical sloppiness is extremely common. Okay, so does this list of vectors span R2? Well, in order to check that it spans R2, I need to check that I can always solve this system of equations, no matter what vector in R2 might be on the right-hand side. Well, we've seen problems like this before, and what we know then is that means that we need to know that this matrix has the existence property. In other words, we need to confirm there's a pivot in every row. To see that they're independent, we need to talk about relations. In particular, we need to worry about whether there are any significant relations, and hopefully there aren't. And said differently, we need to know that this matrix has the uniqueness property. Now, of course, these are the same matrix. Incidentally, in this case. And so in this case, all we need to know is whether this matrix is singular or non-singular. Looking at the determinant easily confirms this is non-singular, so therefore both conditions are satisfied, and therefore this is indeed a basis for R2. Okay. Likewise, let's consider this example. Consider the standard basis vectors in Rn. We've been referring to these as standard basis vectors in Rn for a while. Well, good news, they form a basis for Rn, thus giving us half of our reason why we call these standard basis vectors. They are a basis. And you can argue for yourselves why it is that these vectors form a basis by making an argument analogous to the previous example. And it's just that you end up with this matrix instead of, well, the matrix in the previous example. So, question, is this matrix non-singular? Well, it's very clearly non-singular because not only is its reduced row echelon form the identity, but it itself is the identity. That makes it clearly non-singular, and therefore we have here a basis. Okay, next example. Now there's a temptation for students to look at these last two examples, and you look at, well, look, we needed this matrix to be non-singular, and in this case here we needed this matrix to be non-singular, and so surely, come on, all you have to do, it would seem, is take the vectors in question and make those the columns of a matrix and check if that matrix is non-singular. And it's not that simple. In particular, in these two examples, we were looking for bases of the entirety of Rn, R2 in this case, Rn in this case. And that's not always the case. So consider, for example, here a pair of vectors. Let's ask, is this a basis for this plane, the subspace of R3? Okay. Well, to decide, we need to first check, is this a linearly independent list? And certainly we would need the previous arguments that we've used. We could reduce it down to the question of whether or not this matrix has the uniqueness property, and it does. Some details for you guys to check on your own. But for the span question, we do not need to check if this matrix has the existence property. Side note, it does not have the existence property, but more importantly, that's not what we need to check. We're not responsible for that because we are not responsible for making every vector in Rn a part of this span. We're only responsible for checking that every vector in this plane is in that span. So, different question. So, in particular, I don't need to check that this can equal to every vector in Rn. I just need to check that that can equal to every vector that satisfies this equation. And not hard to persuade yourself that every vector that satisfies that equation is of this form. Certainly, whatever these two values are, this has to be the value that this equation says it has to be. Okay, so all solutions are of this form. Okay, so we don't need the coefficient matrix to have the existence property. We just need this specific system of equations always to have solutions. Again, not the same thing because this is not an arbitrary number. That's not a B3 that could be anything. That is specifically minus B1 minus B2. So when you row reduce that, take this system and row reduce, what you will end up with, and this is a good exercise for students to do on their own, you will end up with a bunch of junk here and a bunch of junk here. And the big mystery question is what will be here? And as it turns out, 0. So we're not, again, not required for there to be a pivot in every row, and there's not a pivot in every row. What we are simply required to confirm is that there are no contradictions, and even though there is a row of zeros, there's no contradiction. So there's no problem here, and there will always be a solution to this system of equations, and therefore this is a basis for this plane. So there's an alternative method that you could use to draw this conclusion. This is just a different way of going. All else being equal, I think what I'm about to show you is not as good. But in order to show that all vectors of this form, again, that's all the solutions to that system, to show that all vectors of this form are in the span of these two vectors, the little tricky move you can pull is observe that, well, this is equal to that, and therefore this is a linear combination of these guys. And so if I simply confirm that both of these are linear combinations of these, then the result works. Right? So if this is a linear combination of those vectors, and if this is a linear combination of those vectors, then what we have here is a linear combination of linear combinations of these vectors, thus showing that this is a linear combination of those vectors. So if you don't like the argument above, the point is you can simply look at these two systems and just confirm that there are solutions to both of these explicit systems, and that confirms the result. Like I say, it's a little bit more trouble this way. It's not clear that this is a win, but it's an alternative.